So now let's understand mathematically this a little bit. We have this, right? Two pieces, one piece alpha initially pure A, the other piece gamma. Okay, put them together. Initial phase boundary at this red line. After small time dt, the interface moved by a little bit dx to this blue location. Okay, now let's understand this a little bit. The change in total amount of B, the change in total amount of B within dx, within here. The change in total amount of B within here, I'm going to draw it, we call it delta B as CB gamma minus CB alpha times dx. The interface moved a little bit. Initially, the concentration would be I'm alpha phase, right? And after it moved, I'm in like this location. Initially, it's in what phase? Alpha phase. But after interface moved, it's in after interface moved from to the blue one. Now it's this same location would be in which phase? Gamma phase, right? So initial concentration CB alpha, final is CB gamma. The concentration changes, and then times dx. That tells me the total amount of solute that changes within this dt, within this dx location. Okay? But then from so-called flux point of view, from flow of point of view, the change in solute atom within here, I'm going to write it as this one. The change in solute B would be, I'm writing what? D times concentration gradient, that's flux, right? Times dt, the flux times time into the material minus the flux out of this section. D gamma, the diffusion of the stuff within gamma phase times local concentration gradient for within gamma times dt minus alpha. So kind of like we are considering this part. Some are flowing in, some are flowing out. I'm just doing the subtraction of flowing in minus flowing out. Make sense? Flowing in, the B would flow, diffuse from gamma into alpha, and then from alpha into, of course now it's kind of like further away. Okay, and then we put a dt towards the end. We are going to have this one, negative sign become positive, negative, negative, right? Now we put alpha in the front, gamma at the end, and the dt we put towards the end. Okay, then we have delta B, we can write these two equations what? Delta B, we can put these two equations together, and we can write dx over dt would be this thing divided by the difference in concentration. Okay, that just tells us dx over dt. And what is dx over dt? It's kind of like the velocity of this interface motion. Okay, and if we introduce similarly to the so-called Boltzmann transformation, the lambda term that relates location and time together, and similarly we do the transformation of concentration with respect to what? Location, become dc over d lambda, partial of lambda with location. dc over d lambda we keep, but what is lambda? Lambda is x over square root of t, and we are only doing this differential for with respect to x, which means t is a constant, right? Now we put square root of t in the front. Partial differential of x with respect to x is 1, so dc over d lambda. Okay? So then we have the partial differential term within the bracket. And then this is what we have from previous. We did the transformation. Concentration with respect to location become c over lambda derivative times square root of t. And then we are going to simplify again. Because the concentration in each of the phase at the interface are constant. Right at the boundary, the concentration in alpha and in beta, they are essentially constant, determined by the so-called phase boundary. The dc over d lambda, the concentration change with respect to my simplified lambda is a constant that depends on concentration. How does the concentration change with my chosen parameter lambda? It's a constant. As a result, we can rewrite the previous equation, which is this one. How fast does the interface move? dx over dt is 1 over the difference in concentration times this term. And because we said the concentration with respect to x is constant times dc over d lambda, and if dc is d lambda is also the same, we would have the velocity of the interface movement is proportional to square root of t. It comes from here, square root of t. Okay, and if we do integration on both sides, we are going to dt put to the right side. We're going to have the location would be a function of square root of t. In another way, it's x squared would be something, a constant times t. And if we're going to plot x versus t, how would you draw it? If x equals square root of t. Not a straight line, right? And also not a concave up. It's actually something like this, so-called the typical parabolic function, parabolic law. Okay? And which means the motion of the interface with time would follow a parabolic relationship. Okay, and let's just stop here.